Welcome to ST Microelectronics tutorial on Power MOSFET Parameters. In this session, we will review the basic static datasheet parameters, avalanche ratings, and thermal parameters described in most MOSFET datasheets. Let's look at three fundamental characteristics of the Power MOSFET and their respective temperature dependencies. First, the drain-to-source breakdown voltage. This parameter should be specified with 0 gate-to-source voltage to ensure that the device is in the off state. The breakdown voltage must be defined by a condition of allowable drain current flow, in this case 1 milliamp. It will always be specified as a minimum value. Here is guaranteed no more than 1 milliamp of drain current at drain voltage up to 400 volts when the MOSFET is at 25 degrees Celsius. Above this voltage, the MOSFET may enter an avalanche condition whose details will be discussed later. The curve traced in the lower left corner shows this behavior. The temperature dependency of the breakdown voltage is positive, so that as the junction temperature increases, so does the breakdown voltage, in a linear fashion, often up to an improvement of 10% or more at maximum operating temperature. Some datasheets will emphasize the breakdown voltage rating at maximum junction temperature rather than 25C, so as to improve the first impression of the device capability. So be sure to check in greater detail when comparing one MOSFET to another. Next, let's review the gate threshold voltage, VGS-TH. This is a commonly misunderstood parameter. The device is tested with the gate and drain connected, while the voltage source increases the voltage until a specified drain current begins to flow. Here we can consider the device to no longer be off. It's conducting current far greater than leakage current. However, it is certainly also not fully on in the true sense of a power MOSFET. The threshold voltage is simply the minimum voltage that initiates some drain current flow. To fully enhance the device, a larger voltage must drive the gate, as we'll see when describing the RDS-on rating. VGS threshold has a negative temperature coefficient as plotted in the lower right. One must take this into account when designing the gate drive circuit to avoid phenomena such as Miller capacitance-induced gate turn-on. Lastly, one of the most important parameters in specifying any power MOSFET, the drain source on resistance, or RDS-on. This is the most critical parameter affecting conduction losses in the application. It should always be specified at a defined gate voltage and drain current, as well as with a defined maximum at 25C. The gate voltage test condition ensures the MOSFET is fully saturated and no longer operating in linear mode, as signal amplifying MOSFETs are operated. Test drain current must be specified since the RDS-on is not constant with respect to this current, as seen in the graph in the lower left, commonly found in most MOSFET datasheets. The RDS-on has a positive temperature coefficient shown in the lower right graph. This curve is also plotted in the datasheet. The RDS-on can increase by well over 2 times at the maximum operating temperature, so it is quite important to take this into consideration during system design. Let us switch our discussion to the avalanche condition, which may occur when the drain-to-source breakdown voltage is exceeded, and the 2 failure mechanisms associated with it. Avalanche characteristics are typically a uniquely defined set of absolute maximum ratings within the MOSFET datasheet. Avalanche begins when a critical electric field is reached that causes a positive feedback loop of carrier concentration, called the avalanche effect. It is not necessarily a destructive phenomenon, but must be bounded by some maximum values to maintain the reliability of the device. Within the avalanche characteristics table, we often find 2 parameters, the maximum allowed avalanche current, or IAR, and the maximum pulsed avalanche energy, or EAS. The IAR is defined by the maximum current during an avalanche condition that avoids latching of the parasitic bipolar transistor in the MOSFET structure, and the subsequent degradation of the MOSFET voltage blocking ability that follows. Since bipolar latch-up can occur at any time that this current is exceeded, IAR is considered a limit in both repetitive and non-repetitive conditions. Operation below the IAR value can be considered safe. EAS is a temperature-dependent value. It is defined by the maximum amount of energy that can be dissipated in the MOSFET during avalanche without exceeding the maximum rated junction temperature. In most cases, the starting reference temperature of the die is 25C, so should avalanche occur at different operating temperature, this value will change. Often there is a graph of avalanche energy versus junction temperature to assist with this calculation. Since repetitive avalanche conditions result in a dynamic thermal profile for the silicon, the IAR can only be specified for a single event. Now that we've seen how temperature can have a dramatic effect on MOSFET parameters, let's take a closer look at the thermal parameters specified in the datasheet and how to interpret them for design considerations. In all instances, these resistances are used for design considerations to keep the internal silicon junction below its absolute maximum rated temperature, or TJ. Otherwise, the device is subject to degraded performance, reliability, or even failure. Thermal resistance is a measure of the power dissipation needed to cause a rise in temperature between two materials. Often the MOSFET datasheet will specify two such resistances, the junction to case resistance, RTHJ to C, and junction to ambient resistance, RTHJ to A. For packages that are not readily attached to a heatsink or with low thermal resistance to a solderable pad, such as an SO8 or TO92, you will usually only find the junction to ambient resistance specified, as the case is not thermally controlled by a mass like a heatsink or PCB. The junction case resistance refers to the die specifically. It can be interpreted as the thermal resistance when the package is held at a constant temperature or mounted to an infinite heatsink. In this case, the junction temperature will rise linearly with power dissipation above the case temperature, as specified by the junction to case thermal resistance. It is typically lower as the silicon die increases in size. The junction to ambient resistance is defined by the package and is seen as the relationship between case temperature and power dissipation as the device sits in still air. In this condition, the power dissipation allowed by the maximum operating junction temperature tends to be low enough to consider the case and junction temperatures as approximately equal. It's important to note that the thermal resistances are specified under continuous dissipation of power, but we know that power dissipation can often come in short pulses during switching operation. For this reason, we define a transient thermal impedance, ZTH, as seen in the graph on the right. It can also be defined as a multiplication factor of K that scales the thermal resistances already defined. Short duration pulses of power dissipation affect directly the silicon only, and the thermal impedance is defined largely by the properties of the silicon and its dimensions. As the pulse duration increases and the thermal capacitance of the silicon saturates, we now define the impedance based on silicon size and the thermal capacity of the preform attaching the die to copper. Finally, we see a thermal equilibrium reached at long time scales as the internal thermal capacitances are all saturated. The total resistance is defined by the characteristics of all layers of the package in silicon. The resulting graph we use in practice is shown here, the thermal impedance chart. It's applicable to single pulses as well as repetitive ones that are defined by the pulse duration and duty cycle. As the operating conditions approach DC, you'll see that the thermal impedance approaches the defined continuous operation thermal resistance junction to case, R theta J to C. That concludes our tutorial on MOSFET parameters and thermal considerations. Thank you for listening. For more information, please go to www.st.com.